So over a range of pi minus delta phi by 2 to pi plus delta phi by 2, what is the probability of finding the light atom? So for that, we the probability of finding the light atom over a range that we are defining, we have to integrate it over the range that we want to, which is pi minus delta phi by 2 to pi plus delta phi by 2, and okay, delta phi by 2. Our wave function psi, the psi of phi, the normalized wave function is root 1 by 2 pi e raised to I phi, right? So psi star of phi, psi of phi into d phi. The only difference between the previous derivation is we are supposed to evaluate the integral and find what is the value of the integral over that same range. The integration is going to be the same, just that the and also the range at which we integrate is also different here. So this is going to be I'll just write it as a and b for the simplification of the calculation, where a is equal to pi minus delta phi by 2 and b is equal to pi plus delta phi by 2. So this is going to be 1 square root of 1 by root 2 pi e raised to complex conjugate of psi of phi is 1 by square root of 1 by 2 pi e raised to minus I phi. So that's what we write here. Psi of phi is given by 1 by square root of 1 by 2 pi e raised to I phi into d phi, and we'll take out 1 by 2 pi's together, 1 by square root of 1 by 2 pi outside the integral, and since there are two square root of 1 by 2 pi, this will become 1 by 2 pi, and we'll integrate over a to b e raised to minus I phi e raised to plus I phi d phi. This is going to be e raised to 0. So 1 by 2 pi a to b e raised to 0 is equal to 1, so a to b d phi. So 1 by 2 pi phi ranging from a to b, where a is pi minus delta pi by 2, right? So 2 pi is b minus a, and we know that b is pi plus delta pi by 2 minus a is pi minus delta pi by 2, so minus pi, minus of minus delta pi by 2 is plus delta pi by 2. So these two will cancel out, and the remaining will be 1 by 2 pi delta pi by 2 plus delta pi by 2 will become delta phi plus delta phi by 2 plus delta phi by 2 will make it as plus delta phi, and this is the probability of finding the light atom in the range of delta phi at phi is equal to pi. So this is the probability. So this is going to be 1 by 2 pi delta phi. So our next question is to find the probability of the light atom between phi is equal to pi by 2 and 3 phi is equal to 3 pi by 2. So we have found that this is going to be this is going to be 1 by 2 pi into delta phi, right? So pi by 2 is pi minus pi by 2. 3 pi by 2 is pi plus pi by 2. So here delta phi is equal to pi, right? Which is pi plus pi by 2 minus pi minus pi by 2, which means delta phi is going to be pi. So we wanted to see what is the probability of finding the electron for this range. So it is going to be is equal to 1 by 2 pi into delta phi. Here the delta phi is 1. Delta phi is equal to pi. So 1 by 2 pi into pi. So this will become 1 by 2. So yeah. So the first question was to normalize the wave function. We normalize the wave function using the property of wave function, which is being written here. Over the whole space, the probability of finding the particle is going to be 1 minus infinity to plus infinity. Since we have defined the wave function over a range of 0 to 2 pi, we change the limits to 0 to, we change these limits to 0 to 2 pi, and the wave function is written as e raised to I phi. Psi of phi is e raised to I phi. The complex conjugate of it is e raised to minus I phi. And when we substitute this, and since there is a normalization, we have also substituted a pre-factor, which is the normalization constant for the first calculation, and we found by substituting this wave function and its complex conjugate to this particular equation, we were able to calculate what is the value of C, and which is the normalization constant. That's what we have been asked to calculate in the first part of the problem. The second part of the problem is to find what is the probability of finding the light atom in the range of a delta phi around phi is equal to pi. So for that also we have to find the probability density of finding a particle is given by an integral of psi star of phi, psi of phi, d phi, and by evaluating the integral we were able to get the, for a range of pi minus delta phi by 2 and phi plus delta phi by 2, we were able to get by evaluating the integral we were able to get the probability is 1 by 2 pi into delta phi. So in the third problem is sort of a extension of the second one, where we have been for a particular they have been given a particular range where phi is equal to pi by 2 and phi is between the range of phi is equal to pi by 2 and phi is equal to 3 pi by 2. What is the probability of finding the particle? So for that we have found out what is the delta phi, the difference between the difference between the two edges of the range. The delta phi is going to be pi, and once we substitute delta phi as pi in the equation that we have gotten from the second part of the problem, we have calculated that the probability of finding the light atom between phi is equal to pi by 2 and pi is equal to 3 pi by 2 is 1 by 2. Now the next thing that we have come across while we have been discussing about the postulates of quantum mechanics was about the commutators. So we first come across the operators, and we came across operators can commute. So there is a problem in the problem set assignment that due today is to find the commutator of Lx and Px, if I remember correct, or Ly and Px, if I remember correct. So this is something which will help you to find how is a commutator being calculated or not. So here we have been asked to find what is the commutator of x cap and px cap. X cap is the position operator and it is equal to x. Px cap is the momentum operator, which is minus I h cut del by del x. And we have been asked what is the commutator x cap px cap. So this is how a commutator is being denoted: x cap comma px cap inside a square bracket. So this is called commutator of x cap px cap. So this is being defined as x cap into px cap minus px cap into x cap. So let's substitute what is x cap and px cap. X into minus I h cut del by del x minus I h cut del by del x into x. So this is going to be x. There is nothing to here there is nothing to evaluate, so we can just directly write it back as px cap minus of minus is going to be plus I h cut del by del x of x. Del by del x of x is going to be 1, right? So x px cap plus I h cut. So this is the commutator of x cap and px cap. X cap is the position operator and px cap is the momentum operator. So in the problem set, we have been asked to find what is the commutator of Ly cap and px cap, if I remember right. So I don't know how many of you are familiar with angular momentum operator L. So let me explain what is angular momentum operator. I won't be explaining the commutator of x cap and px Ly cap and px cap. Cap is to I forgot if I have mentioned what is why do we mention it with cap. So cap just denotes that it is an operator. So yeah, let me just explain how we calculate Ly cap. So L is angular momentum operator. This is a L cap in general as an angular momentum operator. And it has been defined as Lx cap Lxi cap, Lyj cap, K cap. And yeah, if we want to find what is so how do we know what are the values associated with Lx, Ly, Lz? So L is basically R cross P, where R is Xi cap, Yj cap, Zk cap, and P is the Pxi cap, Pyj cap, pz k cap, and we'll calculate the L vector or L cap vector depending upon whether it is a unit vector or it's not a unit vector. So this can be written as ijk xyz px py pz. So I cap into ypz minus zpy minus, so this will, every odd ones are like plus, and the even entry of the columns will be minus. So it's going to be minus j cap, and in this particular case so minus j x into pz minus z into px plus k cap. This is the odd entry at the odd column, so it is k plus k cap x into py minus y into px. Okay, now we have to make it as I cap ypz minus zpy. We'll take this one as this one towards inside, so it will become plus j cap zpx minus xpz plus k cap xpy minus ypx. This is equal to the, so this particular ended thing is going to be L vector, so that will be Lx I cap, Ly j cap, Lz k cap, and we are supposed to get what is the Ly. Ly is this one, zpx minus xpz, and we are supposed to calculate the commutator just like this. How is Ly commutes with px? We are supposed to calculate this. So I just have given what is the equation for Ly, and from L we can evaluate the commutator similarly as mentioned here. Yeah, if you have any questions from the problems that we have discussed so far, please raise it. Okay. The next question is based on the Heisenberg uncertainty principle. So for a particular molecule, it undergoes transition between a ground state and an excited state. So this is a ground state, this is excited state 1, this is excited state 2, and the lifetime of the molecule in excited state 1 is 10 seconds, and the lifetime of the molecule at excited state 2 is 0.1 second. Okay, so Heisenberg uncertainty principle says that delta E into delta T should be greater than or equal to h by 2 pi. Okay, so from this delta T is the one which corresponds to the lifetime of molecule, or lifetime of a particular state, some molecular state. It can be excited state or the ground state. This is the energy, uncertainty in energy. Energy of that molecular state. So delta E and into delta T is approximately equal to h by 2 pi. So we, in the first part of the problem, we have been asked to calculate the approximate uncertainty in the excited state energy. So here the lifetime is for excited state 1, the lifetime delta T is equal to 10 seconds. So we have been asked what is the delta E, what is the approximate uncertainty in the excited state energy. So delta E is equal to h by 2 pi into delta T. So h is Planck's constant. It is given as 6.626 into 10 to the power minus 34 joule seconds. So h is so delta E is equal to 6.626 into 10 to the power minus 34 joule seconds, 2 into pi into delta T. The lifetime was 10 seconds. These two seconds, second and second will cancel out, and this will come to, when you do the math, it will come to 0.105 into 10 to the power minus 34 joules. Okay, for excited state 2, the lifetime delta T is equal to 0.1 seconds. Delta E is equal to h by 2 pi delta T. This is equal to 6.626 into 10 to the power 9. When we do the similar math here, so you can see that there is the uncertainty in the energy has increased as the lifetime has decreased. So 10.5 into 10 to the power minus 34 joules. So when the delta T has reduced, the delta E has increased. The second part of the problem asks us to calculate what is the width of associated spectral lines in Hertz. So we have a ground state and we have two excited state, ES1 and ES2, right? So this corresponds to a transition. Consider this is nu1 and there is another transition, this nu2. We'll have a spectrum, nu versus some intensity. We are looking at what is the natural line width corresponding to nu1 and nu2. So this can be again calculated using Heisenberg uncertainty principle, which says delta nu into delta T is approximately equal to 1 by 2 pi. So this comes from delta E into delta T is approximately equal to h by 2 pi, and we know that delta E is equal to h delta nu, and the h in the right hand side will cancel out from the h in the left hand side. That's why we get the equation like this. Okay, So we have been asked for ES, excited state 1. What is the delta nu? So we know delta T is 10 seconds. Delta nu is going to be 1 by 2 pi into delta T. So this is going to be 1 by 2 pi into 10. This is equal to 0.015 volts. When you do the math, it will be 0.015 volts. For excited state 2, delta nu is equal to 1 by 2 pi into delta T. Here delta T is 0.1. This will be 1.5 volts. So when you increase the delta T, delta nu will reduces. So when the lifetime increases, the line width will be shorter. And also when you increase the delta T, the uncertainty in the energy is also reduced. So in this is a problem which is based on Heisenberg uncertainty principle, and in this problem we have been asked, so we have been given lifetimes of excited state, 2 excited states, and we have been asked what is the approximate uncertainty in the excited state energies, and what is the approximate width associated with the spectral lines of those particular transition in the spectrum in Hertz. So we used these two formulas to basically the Heisenberg uncertainty principle, this particular formula using which we calculated what is delta E for excited state 1, what is the delta E for excited state 2, and from this particular equation we can derive an equation where delta nu and delta T are correlated, and using this we can calculate what is the natural line width, width of those spectral lines associated with those particular transition in Hertz. The last problem that I would like to address today is about the Boltzmann distribution of it relates to the population of different states of different molecular states. So we have been asked to calculate the energy difference between ground and excited state of electronic energy levels of a chromophore where the resonant wavelength of transition is 450 nanometer. So this says that there is an electronic ground state and there is an electronic excited state, and the transition between the ground state and the excited state is resonant to a wavelength 450 nanometer. So what is the delta E associated with it? What is the energy difference associated with it? E ground minus E excited state, or the other way. Sorry. E excited state minus E ground state. So this is going to be equal to hc by lambda. So h is 6.626 into 10 to the power minus 34. 3 into 10, this is in joule second. 3 into 10 to the power 8 meter second inverse. Lambda is 450 nanometer So 450 into 10 to the power minus 9 meter. 1 nanometer is 10 to the power minus 9 meter. When you do the math, it will come to 4.4 into 10 to the power minus 19 joules. So for electronic energy levels, the energy difference between the ground and the excited state is 4.4 into 10 to the power minus 19. The second part is to calculate what is the energy difference between the proton nuclear levels, energy levels of a proton in that particular chromophore at an NMR spectrometer with 600 megahertz frequency. So here the radio frequency that will be applied to perturb or to excite the magnetic to the nuclear excite the nuclear energy levels is 600 megahertz, which means your delta nu is 600 megahertz. So 1 megahertz is equal to 10 to the power 6 hertz. So 600 into 10 to the power 6 hertz. So the energy gap can be calculated. Delta E can be calculated as delta, H nu or H delta nu. So this is 6.626 into 10 to the power minus 34 joules seconds. 1 hertz is 1 second inverse. So this is 600 into 10 to the power 6 second inverse. These two, second inverse and second will cancels out, and this will come as 3.95 into 10 to the power minus 25 joules. So the energy gap in between the electronic levels are in the order of 10 to the power minus 19 joules, whereas the energy gap between nuclear energy levels is 10 to the power minus 25 joules. Okay, now we have to calculate what is the relative population of electronic energy levels of chromophore at 298 Kelvin, which is 25 degrees Celsius, which is around room temperature. Okay, so the relative population is given by n by n0 is equal to e raised to minus delta E by kBt, where kB is Boltzmann's constant this is equal to 1.38 into 10 to the power minus 23 joules Kelvin inverse, joule Kelvin inverse. So for electronic energy levels, n by n0 is equal to e raised to minus, so for electronic energy levels it was 4.4 into 10 to the power minus 19. 4.4 into 10 to the power minus 19 divided by 1.38 into 10 to the power minus 23 into 298 is the temperature. So when you do the calculation, it will come down to 3.39 into 10 to the power minus 47. This means that your N is very less populated compared to your ground state. N is the number of the population of molecule in the excited state compared to the ground state. So the relative population of the excited state is very much lesser than the ground state, N0. That's why it is when N by N0 is very much less than 1, which means your excited state is very much less populated than ground state. Okay, now let's look at how it is for proton nuclear here. N by N0 is equal to e raised to minus 3.97 is the energy difference delta E into 10 to the power minus 25 divided by 1.38 is kb. 1.38 into 10 to the power minus 23 into 298. This will come down to 1.0009. This means that your ground state is almost similarly populated as excited state is almost similarly populated as your ground state. So which makes the nuclear spectroscopies more less sensitive compared to the electronic spectroscopy, because when you have like higher energy, higher population difference between the ground and excited state, that's when you observe better sensitivity. So since the electronic in case of electronic energy level, the excited state is very much less populated than the ground state, so it is more sensitive. It's a more sensitive spectroscopic method compared to nuclear spectroscopy, because in nuclear spectroscopy both the ground state and the excited state are almost the same populated. So yeah, so that's all. That conclude the problems that I want to discuss with you today. If you have any questions with the problems that I have discussed today, or the or any other questions that is pertinent to the last week's portion, I would be happy to answer. You can also type down your questions in the chat box. I'll be able to follow it up. Yeah. Yes, Yashwant. Okay, which question in the assignment? Okay. Yeah, Yashwant, you can unmute yourself and ask the question. I'm sorry, I can't hear anyone. Someone is speaking. Yashwant, please ask the question by unmuting yourself. Okay, please type down the question or just mention which question number at least. Okay. Okay. So you want to know how to find the commutator of Ix and Py. I don't think so. I have found a question where you have to find what is the. Okay, I haven't. Okay, I haven't checked the options for that particular question. One thing you can do is once you are done with the assignment, you can send a mail to the instructor, or you can also post it in the group, in that in the SWIME portal itself, because I won't be able to address anything regarding the framework of the assignment or framework of the question, because I'm not the one who is setting the questions or grading the assignments. I can only help you with some problems that you're facing while understanding the assignments, or um, while while solving the assignment. So I can only help you with that. If you have any problems with the structure of the assignments or any answer options or like the answer key of the assignment, you have to directly contact the instructor or the official TA of the course. I hope it is clear. You can also post the same thing in the SPIME portal, where which is the discussion board. Okay. Any other questions from others? Yes. Okay. Electronics spectroscopy, absorption spectroscopy and all. Yeah. Can you please explain assignment 1 question number 15? Okay. Uh, okay. I don't have assignment 1 question number 15 at this point of time in my hand. I'll check that, and we'll discuss about it next in the next problem solving session at the beginning itself. Is that okay? Yeah, I'm not able to open the current assignment itself. I'll check and get back to you in the next tutorial. I'm sorry about it. I won't be able to do it now. If you remember what is that particular question, or if you can type out what is that particular question, that would be great. But the ambient would be to explain it at the next tutorial session at the beginning. If you all don't have any other question, let's end the session for today. Okay. So this has been explained in the so this particular okay. This particular question has been what is the Doppler shifted wavelength of a green traffic 550 nanometer? I think this a similar question has been explained um, in the class, right? Where one second. Where a Doppler shifted wavelength. Yeah, where a Doppler shifted wavelength of red traffic light approach 660 kilometer per hour. What is the Doppler shifted wavelength for a red traffic light approached 60 kilometer per hour, right? So that has been calculated by a delta delta is equal to, okay, maybe I should write down the equation for you. In class we have, okay. Yeah, so there is a question in the chat box regarding the Doppler shifted wavelength. Let me write it in one of the clean pages. Yeah, maybe here. One of such problem has actually covered in the class. I'll come back to the question about Heisenberg uncertainty principle in a bit. First, let me finish about Doppler shifted wavelength. So Doppler shifted wavelength delta lambda is given by delta naught nu by c, where um, so delta naught will be the wavelength that is being given. Mu and C will be the Yeah. But you want to know what is the new, right? Not new, it's weak. It's sorry, it's not new, it's V, right? Yeah. So it's pretty straightforward, which you can calculate from the equation that is given in the class, right? What is the query about Heisenberg uncertainty principle question? Okay. Hmm. So there are two versions of the Heisenberg uncertainty principle, right? P is greater than or yeah, h by 2 pi, right? So from here only you have to calculate delta P should be equal to h by 2 pi. So using this particular equation, you have to calculate what is the uncertainty in delta P. We already know what is delta x, and we have to calculate what is the uncertainty in delta P. Mhm. Yes, yes. Mm, one second. I might would have okay. One second. Yeah, should be the other way. Yeah. Yeah, from this we should be able to calculate, right? What is uncertainty in its momentum. Okay. Velocity and the mass. Yeah, so I don't know whether it is particularly required about whether the information about velocity and mass is particularly required. Because okay, okay. Yeah, I'm not sure about it, Yeshwant. Uh, I don't know. I personally haven't solved this particular question. Yeah. So one thing is that if you really feel that that is particular way to solve this problem, you can write a mail to the instructor regarding that. Mhm. 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 I think in this particular case, you have to Um, mhm. Mm. No, I'm not sure about it, Yashwant. One thing that I can do for you is, can you just type out your mail ID here? I can get back to you in a couple of minutes. Yeah, yeah, I can get back to you in a couple of minutes or 1 hour. Yeah, yeah. Okay, Yashwant. Okay, let's end the session for today. Yashwant, can you please type down your mail ID? Yeah, great. Thanks. Thank you, everyone. Let's end